So we want to find it's called the general solution of dy dx equals y squared. Okay, so if we start with dy dx equals y squared, we apply that technique, so this is dx dy is 1 over y squared, and in fact we could work here with the integral of dx equals to the integral with respect to y of 1 over y squared. That 1 over y squared is y to the negative 2, and that's going to give us x equals the antiderivative of that power, right? So this becomes y to the minus 1 over minus 1 plus c. In other words, we have x equals minus 1 over y plus c, and then what we would like to do next is solve for y. So we're finding solutions, but the function that is the solution to the differential equation at this step, we just need to do one of those algebraic equations, right? So in doing so, we say, you know what, we're going to move x, z, that constant here, x minus c equals minus 1 over y, and this would lead to y being minus 1 over x minus c. You could write that multiplied by negative 1 both in the numerator and denominator, and this would take the form 1 over c minus x. Okay? Now, this as a function of x so we note that y of x being 1 over c minus x has domain as the following domain. From is an expression defined from minus infinity to c and from c to positive infinity. However, this expression is not defined at x equals to that constant c. Okay, so this has that's one way of writing what this domain is in terms of excluding the value at which this denominator becomes 0. I am going to comment on the following example, and I'm going to leave the details that are more. I just want to comment on the setup of the example, okay? Because I want to mention a couple of things. So. Yeah. Can you read this? Yeah. So this example is relating to acceleration, and therefore to velocity, okay? And so the idea would be to set this up in terms of the distance traveled. Maybe I should give you time to read this, but I'm hoping that you're reading while I'm talking and multitasking, right? So, and one thing here to keep in mind is that the setup is not first order. The setup here would be is second order. Okay. The problem is mentioning some information about how this vehicle is accelerating, and then there are initial conditions, but there are initial conditions with respect to the first derivative and also with respect to the value of the function, right? So the setup of this problem. So now I switch to what was structure camera. Yeah. So in the setup of this problem, the problem looks like this. First, here is assume that x is a function of time. Instead of writing y as a function of x, is assume that x is a function of time. Second, the problem says that there is information on the second derivative of x being equal to some expression of t. Okay, so this is what you would think as f of t. And there is information about the value of x at 0, and then the value of the first derivative of x also at 0. So this problem with the expression on the second derivative with value, right, this part of the problem here is still something we would consider initial conditions. So, but so far we have discussed techniques for first order differential equations involving first derivative, right? Well, there is one way of going about this, which you can convert this second order problem into a first order problem. You can say, you know what? Let's introduce a new variable. Let's suppose that v is the first derivative of x. Okay, so if x prime is equal to v, then this implies that x double prime is v prime. And so with this notation, this is still all a function of t. So with this notation, then we would write that the first derivative of v is equal to t squared, because that was the information we originally had. Okay, and importantly, we had one of the initial conditions. So we had the second derivative of x is t squared, and one of the initial conditions is x prime at 0 is equal to some value, but x prime is v. So we can write this problem with initial condition v of 0 equals 10. And now that this has this formulation is considered a first order differential equation. When we solve this, we're going to obtain an expression for v, and then we can go back and substitute that expression for v and solve yet another first order differential equation. So you basically save the problem in a way in which you solve sequentially two first order differential equations to come back with the solution of the second order differential equation. Okay?